Well, good morning, guys. Today, we're going to jump in and start talking about mass and energy balance as it applies to fluid flow. This is one of the funner topics, connecting some key concepts. I think it's really important. So we're going to start with mass balances and fluid flow. So, as all good mass balances, we typically start with our key principle, namely garbage in is equal to garbage out. With the question being, how can this apply, or how does it apply to fluid flow? Well, to answer this, what we can do is we can look at a differential volume element of fluid and analyze the flux got some stuff in the chat. So if we're looking at a volume element of fluid, we know we can have mass flow in and out in each and every direction. Assuming that we have a 3-coordinate system that we're basing our analysis on, where we have a delta x, delta y, and a delta z, where we have this differential volume element. So we can also have flow going in, flow coming out, flow going up or down, so on and so forth. Or this can be rho u y, rho u, y plus delta y. This could be rho u z, rho u z plus delta z. So if we were going to officially write out this differential mass balance, we would get an expression that looks kind of like this, right? Rho u x minus rho u x plus delta x. And with regard to delta y and delta z, plus rho u y minus rho u, excuse me, not u, v, because we're not a, these are going to be different vectors. So we're going to use v for the y coordinate, w for the z coordinate. Plus rho w z minus rho w z plus delta z, delta x, delta y equals delta x, delta y, delta z times del rho del t, with this being a partial derivative. And for those of you interested, this is equation 4.1 within the text, looking at that differential volume element and describing the mass balance in terms of the net accumulation. So if we divide by the differential volume element and take the limit as delta x, delta y, and delta z goes to 0, we end up with our differential form of this expression. That's a little cleaner, where del rho del t is equal to negative del rho u del x plus del rho B, del Y plus del rho W, dc, which can be simply summarized as an expression here, which says the partial derivative of density with respect to time over a volume element is equal to the cross product of the gradient associated with the flow over the volume element, which, while nice and elegant and mathematical, it doesn't really tell us a whole lot in terms of being able to derive and apply mass balance principles associated with fluid flow. And so what we can look at least when it comes to incompressible flow, is if we're looking at incompressible flow, we can assume a constant density. Which tells us that this expression equals 0. Which tells us also that this cross product must also equal 0. It simply means
is that the divergence?
This value, a symbol?
Yeah, del dot rho v.
Yes, it is technically the divergence. Yeah, when you're looking at the cross product of that gradient term. And so what it really means is that for incompressible flow, and we're assuming a constant density, there's going to be no net accumulation, such that the fluxes in and out of these elements must be equivalent. Now, in a more applied term, what more often than not that we assume is we can further simplify by assuming one-dimensional flow. Primarily because it's extremely rare when we're wanting to look at multi-dimensional flow. When you think about things like tubes and pipes, all of those can be considered one-dimensional when you're looking at the macro scale and how things flows over large distances and over large time periods. Now, we can discuss the presence of mixing and how that can relate to flow, but for the purposes of what we really look at in detail, well, we rely on the use of averages, which allows us to kind of bypass some of the more nuanced approaches that we can look at through this partial derivative. And so reevaluating the initial expressions, but accounting for one-dimensional flow, we get a much more straightforward expression that says the differential mass flow rate is simply equal to the density of our fluid times its flow velocity times the differential cross-sectional area of flow. Where if we integrate both sides, we're left with an expression that says the mass flow rate is simply the density times the velocity times the area. Where if we look at flow through a pipe, and I asked you to derive a mass balance for this flow through a pipe, what would you initially put down?
M initial equals M out.
M initial is equal to M out. Whereby through application of what we just wrote, that would also equal the initial density, the initial velocity, the initial area is equal to the density leaving, the velocity leaving, and the cross-sectional area of the outlet. Now this equation is extremely important, so I'm going to bring out all the colors for this one. You need, further emphasis on the importance of this. This is an extension and a more applied form of what's known as the continuity equation. So please make sure that you really understand the implications of this. And to further illustrate that, let's look at a weird pipe, so to speak. Where now I have flow through a pipe, but the diameter of this pipe is decreasing over the length of the pipe. Where I have some diameter here, and then another diameter, D2. So the question for you all is, how does the velocity change as the fluid moves along the pipe? Well, I can develop that same mass balance. M1 is equal to M2. Then I can apply what I have in terms of the continuity equation, and I can say rho 1, U1, A1 is equal to rho 2, U2, A2. Now, let's assume, for the sake of this argument, and we have incompressible flow. Which means my density shouldn't change. So I'm left with U1, A1 is equal to U2 times the area. So based on this simplified expression, what can we say about the velocity as it flows through the pipe?
It will increase.
So the velocity will increase. Due to a decrease in the flow area. And so what about the flow rate? What happens to the flow rate?
Mass flow rate and volume flow rate should remain constant.
So the mass flow rate will be constant. And that was one of the first expressions we had written down. M1 is equal to M2. Now, volume flow rate can get a little tricky, which we'll talk about here in a second. But for this case, yes, the volumetric flow rate, which I usually denote as a V dot, which is simply the M over the density, in this case, will be constant.
And that's only because it's incompressible, right?
Exactly. This is only true for incompressible flow. This is not valid for compressible flow. And we'll take a look about it, why, here in a second. So if I have flow through a normal pipe where my diameter at the inlet or outlet are the same, and I have, let's say, natural gas flowing through this pipeline, and it comes in at one pressure and it comes out at a second pressure. And I don't know, it's a long pipe, a 5-mile pipeline of gas moving through the system. Do I expect P1 to be greater than P2, P1 to be equal to P2, or P1 to be less than P2? So do I think my pressure is going to increase, decrease, or stay the same?
Decrease.
You are correct. So I would expect the pressure to be less than P2, right? So the pressure will fall. Mainly due to friction. We'll get to that in a second. Hopefully here in a little bit today. And so if my pressure is going to fall, what's going to happen to my densities? Rho 1 and rho 2. Is rho 1 going to be greater than rho 2? Rho 1 going to be equal to rho 2? Rho 1 is going to be less than rho 2. So my density increase, decrease, or stay the same?
You said the pressure at 1 is greater than the pressure at 2, right?
Yes. Oh, I wrote that incorrectly. I apologize. Yes.
Sure.
So pressure will fall. I circled and did the wrong thing. The dyslexia shows up. Thank you for the correction. So my pressure is going to fall along the pipe. What do you think that's going to do to the density of this gas?
Row 1 should be higher than row 2.
Rho 1 should be higher, right? If assuming an ideal gas for all intents and purposes, even a non-ideal gas is going to have the same issue, right? So P falls, which means rho gets smaller. So my density will decrease. Along the pipeline. Now let's consider, knowing that pressure is going to fall with friction, density is going to fall because the pressure is less. I have that same mass balance, M1 and equals M2, rho 1 U1 A1 is equal to rho 2 U2 A2. So if I have the same pipe diameter, I'm left with the density times velocity is equal to density 2 times velocity 2. So what's going to happen to our velocity of our gas as we move along?
The velocity will increase.
The velocity was going to increase. Right, and this is a special consideration for compressible flow. So keep this in mind. In compressible, I'm going to try to make some space between in and compressible. Actually, it's probably a lot clearer if I just write for compressible flow. There's a lot of implications for this phenomenon as it relates to gas flow, and we'll talk about that here more. But I like giving you guys kind of little pieces of key concepts as we introduce things throughout the course, because it helps kind of put pieces together if you've seen them earlier. So keep this in mind and what it might mean for compressible flow as we kind of move into some more concepts. So let's look at an example in mass balances and flows. We're just going to look at compressible flow. We can assume it's water flowing through a pipeline where we have a really weird system with sections A, B, C, and D. The diameter of pipe A, or pipe section A, is 2 inches. The diameter of pipe section B is 3.5 inches, C is 1 inch, and D is 1.5 inches. So the question is, what are the flow rates of sections B, C, and D, and the velocities of flow sections B, C, and D? So let's take a look at this together, and we can see what we can come up with it. So I've got a system that looks like this. Section A, section B, and we have section C, section D. Where this was, if I remember correctly, 2 inches. This was 3.5 inches, 1 inch, and 1.5 inches. So I have A, B, C, D. My initial flow rate is 25 gallons per minute, GPM. So, do you guys want to look at velocities or flow rates first? I'll let you all help me decide.
Flow rates.
Flow rates? Okay. So for simplicity purposes, we can just look at volumetric flow rates. Since we're looking at incompressible flow, it's going to have the same dependence as in mass flow rates. And so the flow rate of A is going to be 25 gallons per minute. What about the flow rate of B?
Should also be 25 gallons per minute.
Yes. The flow rate of B will also be 25 gallons per minute by continuity, because everything flowing out of A must flow into B. The tricky part comes with the flow rates of C and the flow rates of D. If we looked at a mass balance over these sections, we would say the flow rate of B is equal to the flow rate of C plus the flow rate of D. So it looks like we have one equation and two unknowns. However, there's some additional information that we can apply associated with the flows themselves. Namely, when we're looking at this system, we can redraw it in a way that can kind of help you understand how we can determine the flow sections in C and D. Where in reality, even though there's a split between C and D, a fluid particle flowing through this system isn't going to see the split at all. What it's going to see is something that looks like this. And I've drawn it like this for a reason. A fluid particle is going to either flow such a way that it flows into A, into B, and into C, or into A, into B, and into D. It's not really going to make a choice, so to speak. And so the fluid, as it flows through this system, is going to act as if the split that exists between C and D is non-existent. And so what it really sees is the third section with a diameter of 2.5 inches, with a certain percentage of the flow going to C and a certain percentage of the flow going to D. And that percentage is based off of the relative flow areas between C and D. Does that make sense? Or is that equally confusing? And so how we can determine the flow area or the flow rates between C and D is we would look at the relative area of C over the area of C and D times the volumetric flow rate of B, and the flow rate of D is the relative area of D over the area of C plus the area of D times the volumetric flow rate of B. So by looking at essentially each section's flow area contribution to the whole, we can estimate the amount of flow that would move into that section. Now this is assuming that the pressures are equal in C and D, which if you're going to have uneven pressures, it's going to be a little more complicated, but we'll get into that when we talk about energy balances. And so to find the volumetric flow rate of C, I would say, well, that's pi times 1 over 12 squared over 4 over pi 1 over 12 squared over 4 plus pi 1.5 over 12 squared over 4 times 25 gallons per minute. I do that, I should get approximately 7.7 gallons per minute. And C, which means D is just 25 minus 7.7, or about 17.3 gallons per minute.
Could you reduce that to be just the
Square of the diameters, yes. Yes, you can. You can get rid of the pi's and 4's because they show up in every term. So now we've got the flow rates, 7.7 gallons per minute and 17.3 gallons per minute. So now we can look at the flow velocities. Well, the velocity of A is simply the volumetric flow rate of A over the area, or the cross-sectional area of section A, which would be 25 gallons per minute, GPM. Actually, I'll write it in a way that's easier to understand. Gallons per minute. I'd have to convert this to cubic feet per second. Well, in 1 minute, there's 60 seconds. And in 1 gallon, there's, I can't remember off the top of my head anymore. Quite a bit. There's 7.48 gallons in a cubic foot. And then the area of A is times pi times 2 over 12, so I can get it in feet, squared divided by 4. So you do all that, you should end up in feet per second. So what does this come out to be? Yeah, about 2.55 feet per second. Now let's look at the velocity of B, which is the flow rate of B over the area of B, which is equal to 25 gallons per minute again. That's the same conversions. And then all you need to do is just update the flow area expression, which this should give you about 0.85 feet per second. So the cross-sectional area increases, the velocity decreases. And then for C and D, it's the same expression, 7.7 divided by 60 divided by 7.48. I'm giving you shorthand. Hopefully you understand it just for the sake of time. And then pi 1 over 12 squared over 4, which gives you approximately 3.2 feet per second. And you'll actually find that it equals to the velocity of D, because once again, the fluid doesn't see sections C and D separate, it sees them as one continuous section. And so those flow velocities will be the same. Is there any questions on that example and illustration? Any questions or need for clarification in the application of material balance principles on fluids, and how we got to the continuity equation, how we can use it to do calculations around flow and velocities? You guys just got it?
Seems pretty straightforward. Mass in equals mass out.
It always seems straightforward until you do the homework, and then you're like, Dr. Lopez, what the hell? At least that's what I get from experience.
Dang English units.
Yeah, this is English units or something else. That's to be said. All right. So now let's talk about energy balances, where things are a little more complicated, just a bit. So from 308 thermo, we can derive an expression for the energy associated with a system as a function that looks a little like this. I'll talk about each term in a second once I finish writing it all out. All right, so let's break this down piece by piece. So looking globally, I'm looking at the differential energy coming into the system associated with mass moving into our system. And if you want, we can look at that same, I want to make some, magic box volume element, however you want to call it. Right, where we have some fluid moving in, but now that fluid's bringing energy. And we can also have energy being removed from the system associated with mass moving out of the system. And we could, since we're looking at energy, we can also have heat transfer associated with Q and work being done on the system. So all of those energy flows in and out of the system, along with heat and work, has to equal whatever net change in energy of the system, which is what remains within the box. And in this energy balance, we have various types of energy. U is denoted by internal energy. P is our pressure energy associated with flow. GZ is our potential energy associated with elevation, or our static energy. And U squared over 2 is our kinetic energy. You can also define from thermo that we can state the change in internal energy can be equated with a change in heat, a change due to friction, minus, what is it, PV work, delta P over rho. So if we combine these two principles associated with a differential energy balance and looking at a change in state, we can be left with an expression that looks like this. And it's mainly to eliminate the internal energy term, because quantifying internal energy, for lack of a better term, is kind of a pain. So instead of looking at differentials, we mainly look at change associated between an initial state and a secondary state. And I know my handwriting's getting a little hairy here. Hold on, I'll clean it up in a second. I think there was something in the chat. Let me see if I can pull it up. Yes, I can scroll up a little bit. And like I said, I don't mind going slow here or clarifying anything once again. So we have our differential balance, differential energy balance.
Can I ask something real quick?
Of course.
That P delta, is that 1 over rho or 1 over P?
It's 1 over rho.
Okay.
And this is where it gets, like I said, the P's and the rho's are hard to delineate.
Thank you.
This is looking at changes in internal energy between states. And so we do that by, instead of looking at the differential mass in, mass out, and all that, we change all this to deltas. So it's delta M in, delta M out, delta Q, delta W. We combine that and plug in basically M in minus M out, we get a delta U term. We plug this in for that delta U term. And what we're left with is an expression here. So this is an energy balance expression. Between two states. Where one thing we notice is that, well, hopefully we kind of notice, is we end up with a negative P times delta 1 over rho and a positive P times delta over rho. The delta would show up. And what this allows us to do is cancel and simplify the expression. So these go away. And what we're left with is an expression that looks like this. And I'll rearrange it in a way that makes a little more sense. So I have my delta U squared over 2 term. I have a G delta Z term. I have a delta P over rho term. And then what I'm left with, oh, the heat transfer goes away as well, is a friction term and a work term. Now I get rid of the deltas there for a reason, and I'll explain that in a second. Equals 0. So this is known as the simplified mechanical energy balance for fluid mechanics. Now, a couple reasons why I got rid of the F, the delta F, and just called it F. Friction by definition is a value associated with net dissipation between states. And so the delta is largely redundant. I get rid of the delta for the W because work can be either positive or negative by a standard convention in terms of whether it's being done on or by the system. We'll define that here in a second. So definitely this is one for your equation sheets. I'm just gonna make it known it's really important. A second expression can be derived when we can make assumptions, assuming that no work or friction occurs. We get a more simplified expression that looks like this. And this is our Bernoulli's equation, or the simplified Bernoulli's. The mechanical energy balance in some instances is called Bernoulli's, but this is the also important expression because what it lets us know is that energy is conserved in systems without appreciable work or friction. And what that means is if you're looking at a comparison in energy between two states in a fluid, the energy will transfer itself between one of these three quote unquote states, where we have kinetic energy, we have potential, and we have a pressure, which is like a potential energy, of only it's not necessarily true potential, right? When we're looking at potential energy as a function of elevation, we're looking at delta Z. When we're looking at pressure energy as a potential, we simply just define it as pressure. And so when we're looking at these systems where these energy is going to be conserved, we're really looking at understanding the energy transfer between these two states. Now, jumping back and touching base on work and the convention for work. Work is positive if done by the system. And what I mean by the system, I usually mean like a fluid, the fluid itself. So in this case, we'd be looking at, a turbine, so to speak. And work is going to be negative if done on the system. And in most cases, if we're looking at, we'll be considering pumps and compressors. So definitely important thing to note here. And then last but not least, we can touch base on power and how it relates to work. So the power required in terms of energy transfer into a fluid can be noted by the mass flow rate of the fluid times the work that must be done on the fluid or on the system over the efficiency. So in most cases, this will be negative. In the energy balance. And I will say, don't make it negative here. Because if you say, I ask you, what horsepower requirement of a pump to move fluid A from point A to point B based on certain constraints, if you tell me negative 1/2 horsepower, I'm going to ask if the horse is running backwards. So it gets tricky when we're looking at signs associated with work and power. I like to say that signs don't matter, but some people are picky. I just say make sure it makes sense. And that's why I give you a convention when you're drawing up your energy balances. Got a pump involved, the work is mostly going to be considered negative in terms of when you set up that energy balance. And if it's positive, double check, figure it out. But at the same time, once you've got that negative work and you start calculating power requirements, just get rid of the sign and move on. Power is a little tricky, especially when it comes to English units, because English units likes to make everything hard, makes everything harder. And what I will say, that 1 horsepower, because horsepower is equal to 550 foot-pound force per second. So keep that in mind when doing your conversions. Note the force, and so a lot of times when you're looking at work, it's going to be in foot-pounds. So just make sure you do the necessary conversions a la G sub C to change your pound mass into pound force. All right. Any burning questions, thoughts, things I can help clarify and address?
Can you quickly show that conversion from pound mass to pound force?
Pound mass to pound force, sure. So when you're looking at your energy balances, let me write it up real quick, and I apologize for my crappy shorthand. One thing you want to note, which is why I introduce it in the first day of class, every term must have the same units to do the math. And it sounds silly, but you'll be surprised how many times you're going to be doing homework and you're going to have PSI in one term, feet in another term, feet per second, and it gets messy. So if we look at all of these terms, let's just start with the first term, delta U squared over 2. You have feet squared per second squared, right? Because you have feet per second and it's all squared, so you end up with feet squared per second squared. And that tells you that each of these terms should have units of length squared per time squared, which means your work length is going to be length squared per time squared, which is really frustrating because you're going to say, well, how am I supposed to get foot-pounds out of this? Well, when you're looking at calculating power, a lot of times you're going to have mass times work over efficiency. Efficiency is not going to have a unit, but your mass flow rate is. And so you're going to end up with a pound mass per second times a foot squared per second squared, which is going to give you pound mass foot squared per second cubed. Now, if you take those units, pound mass, foot squared per second cubed, and you divide by G sub C, which is going to be that 32.2 pound mass foot per pound force second squared, you will find that suddenly your pound mass goes away. Your foot becomes a single foot, and your second squared goes away, and you're left with a single second. And then you're left with a foot pound force per second. And so if it'll help, you can, put a G sub C there, just to kind of let you know that that's how you're going to have to make that connection to get the units where it is. And then once you've got the foot pound force per second, then you just say a horse with power is 550 pound force with a foot over a second. Does that make sense? And I'll admit it's confusing and it's frustrating. I didn't make the English unit. I just have to provide exercises and homework associated with it. All right, guys. Thank you all for attending the lecture. Feel free to send me emails or come by office hours today with questions. But if not, take care. Have a great rest of your day.
Thank you.
Bye, guys.
Thank you.
Thank you.
Of
Thank you.
course.
Thank you.
Bye.
Bye.